Look at this raw Java code. Specifically, look at the empty space between these curly braces. Up top, the scanner import acts as an open door. It is the system's entry point for chaotic, unpredictable text input arriving from the outside world. Below that, the curly braces of the class define a rigid boundary. This is the structured internal memory space tasked with making sense of that external input. The engineering challenge here is bridging a gap, taking arbitrary user input and connecting it to a precise, optimized address inside our computer's memory. Whatever logic we write inside these braces will entirely dictate how efficiently our system uses its time and its physical space. To see how that works, we are going to build 3 distinct algorithmic architectures inside this space, each escalating in complexity. Software performance is governed by the structural choices made inside these braces, reaching beyond the raw limitations of hardware like CPU speed or RAM. We start with the simplest architectural injection, instantiating a basic array and a standard for loop to read it. This creates a specific physical layout in the machine, a contiguous, unorganized block of memory cells. We place an active read head at the very beginning, at index 0. Our traversal logic is naive. The read head scans sequentially, moving step by step through the array, checking every single cell, all the way up to n, the total number of items. This loop only halts when the contents of a memory cell perfectly matches the text we fed into our scanner. In computer science, the mathematical concept defining this approach is O of n time complexity. Under an O of n architecture, the time it takes to retrieve an item scales linearly and symmetrically with the total size of the dataset. Searching through a list of 100 items takes a maximum of 100 computational cycles. Searching 1 million items takes 1 million cycles. This exposes a critical vulnerability. As data approaches infinity, linear iteration creates severe system bottlenecks. The root cause of this bottleneck is that the architecture operates with zero prior knowledge about the internal topology of the dataset. It searches blindly. An O of n search, in practice, is a failure of data organization masquerading as a retrieval strategy. To break that linear bottleneck, we absolutely have to impose rigid mathematical order onto our chaotic data. Our next architecture requires a strict prerequisite. The memory array must be pre-sorted before a search can even begin. Inside our class, we drop the for loop entirely. In its place, we write a while loop designed to calculate mathematical midpoints. This is a binary search. The initial step bypasses the array's beginning entirely, dropping the read head directly into the exact middle of our sorted data. The algorithm then evaluates if our target scanner input is mathematically higher or lower than that midpoint value. Because the data is sorted, this single comparison yields a massive efficiency gain, instantly discarding the entire half of the array where the target mathematically cannot exist. From here, the logic repeats. Through recursive bisection, the algorithm continually halves the remaining search space until it isolates the target. This introduces our second efficiency metric, O of log n time complexity. Logarithmic time results in an exponential decrease in the time required to retrieve an element compared to linear scanning. To quantify that improvement, searching 1 million items drops from a worst case of 1 million cycles down to approximately 20 cycles. But this massive retrieval speed requires a trade-off. You sacrifice upfront processing time and energy to pre-sort the data before searching. By enforcing a rigid geometry on the data, binary search discards millions of irrelevant items in a single step. What if we challenge the premise of searching entirely? How could a system locate a piece of data without traversing memory at all? This leads to a third method, the hash map lookup. Its core mechanism abandons traditional search algorithms in favor of direct mathematical computation. Instead of looking for the data, we use a hashing function. This treats the raw scanner input text as an equation, processing the letters to produce a specific fixed integer. That output integer serves as an explicit pointer. It draws an instantaneous line routing straight to one specific isolated memory bucket. This achieves the ultimate time complexity tier, O of 1, known as constant time. Under O of 1, retrieval speed is completely independent of the dataset size. Fetching a record from a database of 10 items occurs at the exact same computational speed as fetching it from 10 billion items. However, this constant time demands a severe spatial trade-off. It requires pre-allocating massive amounts of empty memory space. This sparse array bloat is mathematically mandatory. The system needs extra empty buckets to prevent data collisions when hashing thousands of different inputs. An O of 1 architecture proves that absolute speed cannot be generated from nothing. It is purchased with massive spatial bloat. This chart shows the temporal performance of all three architectures simultaneously, plotting dataset size on the x-axis against retrieval time on the y-axis. The steep diagonal line represents the systemic drag of a linear O of n search. Below that, the flattening curve shows the highly efficient logarithmic scaling of a binary search. At the very bottom, the flat horizontal line represents the constant time of hashmap lookups. These theoretical scaling limits are inherent to the logic we place between those original 3 lines of Java source code. There is no single perfect algorithm. Each architecture is engineered to serve a distinct operational scale. O of n remains completely sufficient for microdatasets, where the upfront setup overhead of sorting or hashing just isn't justified. O of log n is optimal for massive, read-heavy databases that are infrequently updated, making the upfront sorting time a worthwhile investment. And O of 1 is necessary for real-time systems where milliseconds matter, assuming physical memory hardware is cheap and abundant enough to support the bloat. The empty space inside a class acts as a negotiation table. Here, developers constantly trade spatial memory and initialization overhead to purchase processing speed.